Good morning to all. Today, myself Priyanka from Bsc Chemistry Honors Final Year. We are here to discuss the chapter of Inorganic Chemistry, and the name of the chapter is Magnetic Properties of Transition Metal Complexes. So, let's start the chapter. Electrons revolve around the nucleus in every atom. A revolving electron, like a loop of current, was shown by the noted physicist Oersted in 1820 to deflect the magnetic needle. When electron revolves in anti-clockwise direction, the current is clockwise. As a result, the upper face of the electron loop acts as the south pole and the lower face acts as the north pole as shown in the figure 2.1. Thus, an electron in motion behaves as a magnetic dipole and possesses definite magnetic moment. If electron E is the charge on the electron revolving in an orbit of radius r with a uniform angular velocity omega, then the corresponding current produced is I is denoted as the current that is equal to charge upon time, where T is the period of revolution of electron. According to Bohr's theory, an electron in an atom can revolve only in discrete stationary orbits, in which the angular momentum of moving electron is an integral multiple of h upon 2 pi and where h is Planck's constant. Thus, mvr is equals to n h upon 2 pi, where n represents the orbit and can have the values 1, 2, 3 and so on. As we know, v is equals to r omega, where omega is the angular momentum. Substituting the values, we have the magnetic moment is equals to Eh upon 4 pi m. Thus, Bohr magneton is the magnetic moment of an atom due to the orbital motion of the electron in the first orbit of hydrogen atom. Since the magnetic field is produced by the moving electrical charge, it is expected that the nuclear spin, the spin and orbital motions of the electrons will result in magnetic moment. The nuclear contribution is very small compared to the electronic contribution. Therefore, the nuclear contribution can be easily neglected. It means that the measured magnetic susceptibility of pure substances are usually associated with the electrons. Each moving electron can be regarded as a micromagnet, and the total moment exhibited by a substance is the net result of the movements of individual electrons. To define the magnetic behavior of materials, it is appropriate to understand a few terms associated with magnetism. That is pole strength. Pole strength is the strength of the magnet, may be expressed in terms of unit pole. A unit pole is defined as the pole that repels or attracts a similar pole placed 1 centimeter away with a force of 1 dyne. Thus, a unit intensity of magnetic field exists at the point and the unit pole experiences a force of 1 dyne. The another term associated with magnetism is pole strength and lines of force. A magnetic field of unit intensity is considered to give a unit line of force per square centimeter. If a pole of strength m is enclosed in a sphere of radius 1 centimeter, a total of 4 pi m lines of force will come out of this pole. This is because of the surface area of the sphere is 4 pi square centimeter. The number of lines of force per square centimeter at the surface of the sphere is given by 4 pi m upon 4 pi, that is equals to m. Another term is intensity of magnetization. It is denoted by I. It represents the extent to which a sample is magnetized when placed in a magnetic field. It is defined as the magnetic moment per unit volume of the magnet. The formula for I is equals to magnetic moment upon volume. If A is the uniform area of cross section of the magnetized sample and 2L is the length of the sample, then I becomes M by A. Thus, intensity of magnetization of a magnetic material is also defined as the pole strength per unit area of cross section of the material. Magnetic induction. When a substance is placed in a magnetic field of strength H in Gauss or Oersted, the total magnetic induction or magnetic flux density B within the substance is given by the relationship B is equals to H plus 4 pi I, where I is the intensity of magnetization. The ratio B by H is called the magnetic permeability. Magnetic permeability is the ability of a material to permit the passage of magnetic lines of force through it. The magnetic permeability of a substance B by H is the ratio of the density of magnetic lines of force within a substance in a magnetic field to the density of lines of force in that field in the absence of the substance. The ratio I by H is called the magnetic susceptibility per unit volume, or simply as volume susceptibility. It is a property which determines how easily a sample can be magnetized. It is this quantity that is commonly measured experimentally. Magnetic susceptibility is commonly expressed per gram as Xi or per mole Xi m. Thus, Xi m is equals to m by d, where m is the molecular weight and d is the density. The molar magnetic susceptibility is related to the permanent magnetic moment of a pure substance. The permanent moment is expressed in Bohr magnetons. Thus, the magnetic moment, that is denoted by mu b, can be calculated from the magnetic susceptibility using the above relation. Types of magnetic materials. When a substance is placed in an external magnetic field between the poles of the magnet, and the magnetic field produced by the spin and orbital motion of the electrons of the substance interacts with the external magnetic field, different substances show different magnetic behavior when placed in the external magnetic field. On the basis of their magnetic behavior, different materials can be classified into the following three categories. The three categories are diamagnetic substances, paramagnetic substances, and the third one is ferromagnetic substances. Then diamagnetic substances are those substances which are weakly repelled by the external magnetic field, are called diamagnetic substances. Diamagnetism is exhibited by substances which allows the magnetic lines of force to pass preferably through vacuum rather than through themselves, as shown in figure 2.2. We can see here it amounts to saying that in case of diamagnetic substances, the number of lines passing through them is slightly less as compared to the lines of force passing through the vacuum. As a result, diamagnetic substances are slightly repelled by an external magnetic field. Diamagnetism is exhibited by all substances with completely filled electronic subcells. Diamagnetism is produced by the orbital motion of the electrons of the atoms, ions, or molecules of the substances. Diamagnetism effect arises only when the substance is placed in a magnetic field. It is due to the interaction of the applied magnetic field with the magnetic field induced in a substance with completely filled electronic subshells. The induced magnetic field in case of substances with paired electrons is in the opposite direction to the applied magnetic field. Paramagnetic substances are those substances which are broadly defined as substances which are attracted towards the applied magnetic field. The number of lines of force passing through a paramagnetic substance are much more compared to those that would pass through vacuum, as shown in that figure 2.2. Paramagnetism is caused by the presence of unpaired electrons. The more the number of unpaired electrons in a substance, the greater is the paramagnetic behavior. We know that most of the transition elements, including F block elements, are known to contain unpaired electrons. As a result, transition metals display paramagnetic character. All paramagnetic substances have a net zero net non-zero magnetic moment of its own. Some of the common examples of paramagnetic substances are aluminium, platinum, chromium, and copper sulfates, and the salt solutions of iron, copper, and nickel, and dioxygen molecules. Some of the paramagnetic substances show complicated magnetic behavior which arises due to interaction of individual magnetic moments. The individual magnetic moments interacts with one another in such a way so as to align themselves spontaneously. Here we can see the classification of magnetic behavior, that is diamagnetism, paramagnetism and ferromagnetism, and their properties. Experimental methods of determining magnetic susceptibility. A number of methods for determining the magnetic susceptibility are known. The two important methods commonly used are, first one is Guy's method and second is Faraday's method. So let's discuss the Guy's method. This method involves the filling up of finely powdered substance to a certain height in a Pyrex glass tube called the Guy's tube. This tube is suspended from an arm of sensitive analytical balance in a magnetic field. An electromagnet providing a constant magnetic field in the range 5000 to 20,000 Gauss is generally used. The bottom part of the sample is in the stronger part of the magnetic field, while the top part of the tube is in a zero magnetic field. The whole assembly is housed inside an enclosed system in order to avoid vibrations of the suspended samples. A diamagnetic representation of the setup is shown in figure 2.3. Here we can see the figure 2.3, that is showing the Guy's method for determining the magnetic susceptibility. On moving on this chapter, we will discuss this Guy's method. The powdered substance in the Guy's tube is first weighed without the magnetic field and then weighed in the presence of magnetic field. In case of paramagnetic substance, the substance will be attracted strongly towards the magnetic field and will weigh more. This increase in the weight of the substance is a measure of the paramagnetism of the substance caused by the unpaired electrons. The larger the number of unpaired electrons in the suspended substance, the greater is the increase in the weight of the magnetic field. In case the substance is diamagnetic, a decrease in the weight of the substance is registered when the magnet is on. Calculation of magnetic moment by Guy's method. The Guy's method is the simplest of all the methods for measuring the magnetic susceptibility. The method measures the force exerted on the cylindrical sample suspended in a non-homogeneous magnetic field of an electromagnet. The force acting on the sample is given by the expression F is equals to 1 by 2 A, K and H ka square, where A is the cross-sectional area of the cylinder, H is the intensity of central homogeneous part of the magnetic field and K is the volume susceptibility. The above expression of force is applicable only if the measurements are carried out in vacuum. However, since the sample is placed in air, the susceptibility due to air, that is K dash, needs to be subtracted from the measured susceptibility, where K dash is the volume susceptibility of air. The Guy's tube itself is in the form of a hollow specimen and exerts a force which is always present. In order to evaluate the exact force acting on the sample, the force developed due to hollow specimen needs to be subtracted from the measured force. The force acting on the hollow specimen, rho, is negative because the tube is made up of diamagnetic material, where rho is the force developed due to the hollow specimen. For a specimen of constant length and cross-sectional area, the factor AH square is constant. If we take into consideration the density of the specimen, it is possible to rewrite the equation as this relation. where alpha is the constant for the displaced air and is equal to 0.029 into volume of the sample, and beta is the tube calibration constant. Omega is denoted as in the behalf of weight of the sample expressed in grams, and F dash is the force on the sample. Guy's tube is calibrated by filling the tube with a substance whose susceptibility is accurately known. The commonly used substances for calibration is deep blue colored compound mercury tetrathiocyanotocobaltate. Its susceptibility at 20 degrees centigrade is 1.644 into 10 raised to the power minus 7. Once we know alpha, beta, rho and F on a given sample of known weight W, the volume susceptibility Xi can be easily calculated from the equation we have written above. It is important to recall that the susceptibility measured of a given paramagnetic substance consists of contributions both from the paramagnetic and diamagnetic susceptibilities. The contribution due to paramagnetic susceptibility is much larger than the diamagnetic susceptibility. The correct susceptibility of the sample is obtained by subtracting the diamagnetic contribution. Thus, paramagnetic susceptibility is equal to the measured magnetic susceptibility minus diamagnetic susceptibility. Some of the inherent advantages of Guy's method are: it requires very simple, easy to assemble equipment. The second advantage is it is reasonably priced equipment. Third one is it is easy to handle and use. Fourth one is it requires a large amount of substance, thus an ordinary analytical balance can be used to measure the change in mass. Also, here are some disadvantages of Guy's method. In spite of several advantages, Guy's method suffer from the following disadvantages. First disadvantage is it requires large amount of sample. Second one is uniform packing of sample in the Guy's tube is not only tedious and time consuming but is very laborious. Consistent results are not obtained if the packing of the sample is not uniform. Second method for determining the magnetic susceptibility is Faraday's method. Faraday's method requires a very small amount of the magnetic sample. The sample packed in a quartz ampule is suspended from a sensitive balance in a region of fairly strong magnetic field as shown in figure 2.4. The sample is suspended between the magnetic poles so that the value of the product H dH upon dx is constant over the region occupied by the sample. dH upon dx is the gradient of the field. The whole setup is enclosed in a closed system which can be flushed with inert gases like nitrogen and helium. The setup we can see in the figure 2.4, that is for Faraday's method for determining the magnetic susceptibility. A sample weighing 0.1 to 10 mg of the substance taken in a ampule of internal diameter, that is 1 millimeter, is placed in the magnetic field of constant gradient dH upon dx. The force acting on the sample is measured directly using a quartz fiber torsion balance and is given by F is equals to m xi h and the gradient. Similarly, the force exerted by the standard calibrant can be measured by weighing the calibrant both in the field and out of field. Generally, the calibrant used in the mercury tetrathiocyanotocobaltate 2. Since the magnetic field H and the field gradient are the same in case of unknown sample and the standard, the force acting on the sample and the standard can be rewritten as H into the gradient is equals to F upon m into xi, where xi and xis are the susceptibilities of the sample and the standard, m and ms are the respective masses, while F and Fs are the respective forces at constant H into dH upon dx. Advantages of Faraday's method. Faraday's method requires a very small amount of the substance and small sample need not to be homogeneous. Compared to Guy's method, which require larger amounts, this method requires only several milligrams. Faraday's method gives a specific susceptibility directly. On the other hand, Guy's method gives volume susceptibility. In order to convert volume susceptibility into specific susceptibility, one needs to know precisely the density of the sample. It is difficult to determine precisely the density of solids because the values of density depends upon the packing of solids. Here are some disadvantages of Faraday's method. The main disadvantages of this method are the equipment is very delicate and requires great manual skill. Second disadvantage is since only a very small amount of the sample is used, reactions occurring at the surface of the sample will lead to large errors. Then we will discuss about relationship between magnetic susceptibility and magnetic moments. Variation of magnetic susceptibility with temperature Curie and Curie-Weiss laws. We have learned that magnetic susceptibility varies with temperature and is therefore temperature dependent. It was shown by Pierre Curie that the paramagnetic susceptibilities vary inversely with temperature. The above expression stating paramagnetic susceptibilities vary inversely with temperature is called Curie's law. A large number of paramagnetic substances obey this sample law, especially at high temperature. If we plot a graph between xi and absolute temperature T, a parabolic curve is obtained as shown in figure 2.5. However, if we measure xi for a substance at several temperatures and then plot the values against absolute temperature, a straight line with slope c is obtained, which intersects the origin. Curie's law is followed by substances where there is no spontaneous interaction among the adjacent pairs, unpaired electrons. In other words, there is no secondary magnetic interactions between the neighboring magnetic centers. Such a substance is called magnetically dilute. Although a large number of substances display this behavior, many substances give straight lines that do not pass through the origin, rather interacts the temperature axis a little above the 0 Kelvin or little below the 0 Kelvin. Such compounds are stated to obey modified Curie's equation, according to which we can see the graphs for magnetic susceptibility temperature curve, where theta is the temperature at which the straight line cuts the absolute temperature T axis. This modified equation is called Curie-Weiss law. Theta is known as Weiss constant. Taking into consideration Curie's-Weiss law, the magnetic moments can be calculated by the equation mu is equals to 2.828 under root xi into T minus theta Bohr magneton. Then we will discuss about ferromagnetic and antiferromagnetism. We have learned that the magnetic properties in case of paramagnetic substances originate entirely from the individual magnetic centers. It means that there is no secondary interaction between the neighboring magnetic centers. Such type of substances are named as magnetically dilute substances. However, there are some paramagnetic substances in which secondary magnetic interactions exist without the between the neighboring magnetic centers. Such substances are called magnetically concentrated substances. In such cases, the magnetic susceptibility shows dependence on both temperature and field strength. Two such important type of magnetic substances are called ferromagnetic and antiferromagnetic. The dependence of susceptibility of these two forms are displayed in figure 2.7 and 2.8. We can see here the figure 2.7 and figure 2.8. Figure 2.7 shows the magnetic susceptibility temperature curve for ferromagnetic substances, and that is figure 2.8 shows the magnetic susceptibility temperature curve for antiferromagnetic substances. A close inspection of the figure 2.7 reveals that there is some discontinuity in the curve at a temperature marked Tc on the curve. This temperature is called Curie temperature. Above the Curie temperature, all ferromagnetic substances obey Curie or Curie-Weiss law. In other words, above Curie temperature, all ferromagnetic substances behave as simple paramagnetic substances. However, below Curie temperature Tc, the magnetic susceptibility's behavior is different and depends upon the field strength. A close inspection of figure 2.8 reveals a characteristic temperature Tn called the Néel temperature. Above Néel temperature, all ferromagnetic substances follow Curie or Curie-Weiss law and show simple paramagnetic behavior. It is important to note that below Néel temperature Tn, the magnetic susceptibility decreases with decreasing temperature. Magnetic moments. An electron has two types of motions associated with it. One, it's going around the nucleus in an orbit, while the other is spinning about its own axis. Since electron is a charged species, its movement generates a magnetic field. Thus, electron determines the magnetic properties in two ways. The magnetic moment associated with the motion of electrons around the nucleus is called the orbital moment, while the magnetic moment associated with the spinning of the electron on its own axis is called the spin moment of the electron. The resultant magnetic moment is the sum of the orbital moment and the spin moment of the electron. We have already discussed that magnetic moments of the substances are generally expressed in terms of unit called Bohr magneton, abbreviated as Bm. The contribution to the magnetic moment from the spin moment of the electron is called the spin-only moment, that is mu. It is numerically equivalent to 1.73 Bm. The Bohr magneton is defined as 1 bm is equals to Eh upon 4 pi mc. The spin magnetic moment mu s of a single electron is given by the formula mu s is equals to g under root s into s plus 1, where s is the spin quantum number and g is the gyromagnetic ratio. Gyromagnetic ratio, G, is the ratio of the magnetic moment to the angular momentum. In case of free ion, the value of G is 2.00023. For all practical purposes, the value of G is taken as 2. On substituting the values of S as half and that of G as 2, the spin magnetic moment for a single electron comes out to be 1.73 bm, as mu s is equals to z under root s into s plus 1, that is equals to under root 3, and the value of under root 3 is calculated as 1.732 Bohr magneton. For atoms or ions with more than one unpaired electrons, the resultant spin moment is given by mu s is equals to g into capital S into s plus 1, where s is the sum of spin quantum number of the individual electrons. Since the value of g is taken as 2, the equation can be rewritten as mu s is equals to 4 under root 4s into s plus 1. Metal ions of D block elements may have 1, 2, 3, 4 or 5 unpaired electrons, and consequently their spin magnetic moments can be calculated by using the equation. Here we can calculate the magnetic moment for 1 unpaired electron, 2 unpaired electron, 3, 4 and 5 respectively. It is important to remember that the sum of spins of the paired electrons is equals to 0. There is another convenient method for which the spin only moment can be expressed as n into n plus 2 under root, where n is the number of unpaired electrons. The experimentally determined values of the magnetic moments of some transition metal ions are in good agreement with the spin only values. However, in some cases, the experimentally determined values have been found to be larger than the theoretically predicted values. This can be attributed to the contribution made by orbital motion of the electron in addition to the spin only value. In cases where both the spin and orbital magnetic moments contribute, the total magnetic moment is given by the equation mu in s plus l is equals to under root 4s into s plus 1 plus l into l plus 1, where s is the resultant spin angular momentum and l is the resultant angular momentum quantum number. Here we can see the ions, their outer configuration, number of unpaired electrons and their magnetic moments. In case of elements of second and third transition series and particularly the lanthanide elements, the orbital motion is not quenched. This is because the 4f orbitals are incompletely filled and are too far inside the overlying 5s and 5p orbitals. Thus, the electric field of the surrounding coordinating ligands does not restrict the orbital motion of the electrons. Therefore, the magnetic moments of lanthanide ions results from the contribution of both the electron spin as well as the orbital motion of the electron. The intrinsic magnetic moments of atoms and molecules are made up of the vectorial sum of orbital and spin moments of unpaired electrons. Three types of interactions are possible: spin-spin, second one is orbital-orbital, and the third is spin-orbital interactions. In case of lanthanide metal ions, all the three interactions plays an important role. In such cases, the resultant magnetic moment can be calculated by means of Russell-Saunders coupling, that is also known as LS coupling, by the relation mu is equals to G under root J into J plus 1, where J is the total angular momentum, which is